So we are now recording, and today's lecture is on web application design. Ta-da! There we go. We're going to do our slideshow. Okay, web application design. So we'll start with the basics. What is a web app? Well, it has a few defining attributes. It's typically some kind of client-server application, right? So you're the client machine, you're the one who's using it, and it at some point typically grabs data from a server somewhere. So that's the typical setup. Now, of course, you could have a web app that does not involve a server. You just download it and you run it through your browser. But the way they're typically deployed is as some kind of, this kind of client-server application. By definition, it runs within a browser window. So if it's not running in a browser, it's not really a web app. And last, typically runs online, but potentially also offline. So one of the standard examples I used before machines got real fussy about using Flash Player, I'd go on to Angry Birds. I'd go on to Angry Birds and I'd, put the bird in the slingshot and go zoom. That was the web app part of it. And some of these other features were that you have to download the core data involved to play the game in the first place, and you had to download the data for the level. That was the stuff you pulled from the server. But once you had that data, you could disconnect from the server, you could shut down your wireless connection and then play repeatedly because you had all the data you needed to proceed. But if you wanted to go to the next level, you had to reconnect to the server. So typically runs online, but potentially also offline. So key implications of this, well, number one, they're not going to be your heavy duty number crunching applications in most cases. So there are limits on the computing power. If it's running in a browser window, it's not really a specialized standalone application, and it's not going to do all the cool stuff that some applications might. Number two, it's probably designed for some primary purpose, right? So it tends to be a really focused application. So in general, you want to keep these web apps simple, focus on what they're supposed to do and make sure they do it. Functionality generally matters more than aesthetics. Okay, aesthetics are nice, right? You want your app to look pretty, but at the end of the day, the big thing is that it works and does the stuff it's supposed to do. Okay. Also, because it's running in a web browser, should expect different hardware and software, right? Any user can potentially show up on any different kind of device. Could be a Mac, could be a Windows machine, could be a smartphone, could be a laptop, whatever. Lots of different hardware and software possibilities. So you have to allow for that. And last, should tolerate disconnects and or traffic surges. Okay, so what do we mean disconnects? Well, the issue there is if the user suddenly loses a connection, which can often happen if, say, you're using a smartphone or you have spotty Wi-Fi, if the user has to reconnect, re-sign in, start everything from square one every time they disconnect, it's going to be a gigantic pain and people aren't going to want to use that app. Likewise, because it's a web app, it's on some server somewhere, there's a possibility that you could have a sudden influx of users showing up to use it. And because of that, you don't want to be rigid in the number of users you can support. So things like cloud deployments are typical there. The cloud system can then handle any sort of large-scale traffic that might occur. Okay.
Professor, I think
Yes,
your
go
screen's
ahead.
frozen.
Mine is?
It's still on the first slide.
Yeah, I've been talking through the first slide. That's okay.
Oh, okay. Sorry.
That's okay. No problem. See, we'll go to the next slide. Does that work? I hope it did. Okay, good. No problem. So we were there on the first slide talking for a bit. So what we'll talk about then, so we know what web apps are. That's the big thing from that first slide. We know what web apps are. We know how they're typically deployed, some of their standard expectations and how they're deployed. So then we'll go through the design process, some technologies, a little bit about supporting infrastructure and architecture and current trends. And I see that probably the chat window is flashing there. We'll have a break about midway through where I'll pause the recording and answer questions. Okay. So basics of the design process. There's two major flavors of how these applications are designed. One is the so-called waterfall method. The other is what's called agile. And if you took IDS 200 with Fife, you probably did cover that. Or if you've taken project management as a course, you've probably also covered that. So in the waterfall method, the idea is that every stage follows the preceding one. So you complete everything in one stage, and then you go on to the next one. Okay, so your basic stages: planning, figure out what your application is going to do; coding, actually writing the application; testing it, making sure that everything works correctly; releasing it to the outside world, right? You say, okay, here it's finalized, go ahead and use it, we think it's good. And then maintenance, periodic updates, correction of defects, that sort of thing. Now, the problem with waterfall versus agile, as we'll see, waterfall works great if you know exactly what you're doing, and if the specifications aren't likely to change, and if you're not likely to have to go back and rework anything. Agile is better if things are much more fluid and chaotic. Okay, so.
Sorry, Professor, have you moved on to the next slide?
Yes.
The screen is, the slides are still frozen.
That's strange. Okay, we're going to pause that. Okay, so your two basic flavors of project: waterfall versus agile. Waterfall more or less requires a stable environment for the project. Agile does not. We'll talk about them. Okay, so in waterfall, every stage gets completed before the next one begins. And the idea is the whole project gets completed at the end. Now, if you are in a stable environment, that means there's not going to be any duplication of effort. You can finish your planning stage, you have a plan in place, that plan isn't going to change. Then you go to the coding stage. You code it up, right? The specifications for coding aren't going to change. You're not going to try to make it run on new technology partway through the project. Once all the coding is done, you say, okay, here's our application. We're going to test it, and as long as it works, we're not going to go back and do any major overhauls, right? So the testing can proceed with a known quantity and so on. However, this is obviously very vulnerable to specification changes, right? So if midway through you say, midway through the coding stage, you say, our guys who are doing the planning, they missed this very important feature that needs to be included. So we need to go back and rework that and see how that's going to do and see if it's going to have impact on other aspects of this project. So then you go back and do some more planning, then you come back and do the coding. That sort of thing can happen multiple times. Likewise, as you're coding it, there may be some major system vulnerability. So you have to change how it's going to be deployed. And you say, oh, well, that means we're going to have to code it in a different way. And you have to go back and rework that. And then maybe once you've released it for testing, your test people say, hey, there are some key features here that are not working the way they're supposed to. So you have to go back to the coding stage and fix that, or maybe even back to the planning stage. It can be a big problem. So that's the issue with waterfall. If you know exactly what's going to happen, for example, if you're building a road and there's just not a lot of surprises because the process of building a road is pretty well understood, yeah, it's going to work pretty well. But if there's a lot of variability in the environment, then you want to use something more like agile. So the agile methodology, essentially, your project operates in shorter cycles. So it's going to be the same sequence of things in the waterfall method, but it's going to be smaller parts of it. For example, in the first step, you might design the core of the application, right? It won't be pretty. You won't have those wonderful aesthetics or snappy graphics, but whatever your application is supposed to do, for example, maybe you have a, I don't know, some kind of data analytics application. You want to make sure that people can upload a batch of data and perhaps run a couple simple tests on it and display those results, right? And make sure that it works on the standard website that you're using. That would be fine. And then for the next round of the cycle, then you do the same thing with the next feature. You add in some more features to your application, or you test it on a wider range of technology, stuff like that. So in Agile, your project works in shorter cycles. There is inevitably going to be some duplication of effort, but the issue is you won't be surprised. Now, the problem that often happens in a waterfall method for IT projects, there's so much back and forth recursion to earlier steps in the process. Many projects never get finished at all. And at the end of the day, you have, like you've built a bridge 3/4 of the way across the river, it doesn't really have any use, right? The idea with Agile is the very first thing you're going to do is build the entire bridge across the river. So at the very least, you'll have a bridge, right? It might not be a great bridge, given more time and resources, you can make that bridge better. But even if the project stops short due to lack of funding or whatever, you'll still have some hopefully useful tool at the end of it. That's the difference. Is with Agile, you're pretty much guaranteed to have something to show for your effort. With Waterfall and IT projects, a disturbing number of these projects are simply aborted without being finished. Now, again, neither Waterfall nor Agile are inherently better, right? They're both useful in their proper context, but for IT projects, software development, Agile is usually better. In fact, we just had some friends of ours over for dinner the other day, and one of them, she's a project manager, and she was talking all about her Agile stuff. I know that she's like a consulting person for IT, but I didn't know exactly what she was doing on this project. And so, yeah, she was like, yeah, we're doing Agile. Okay, so that happened. Okay, dig in a little bit into the various stages. So in the planning stage, you decide what the app will do, right? And this is typically involves categorizing features as must-haves, should-haves, and would-be-nices, right? The must-haves, the things that your application absolutely requires. The should-haves are things that you expect are going to be in there, but if something happens to cut the project short, maybe they don't. And the would-be-nices are things that happen. For example, if your project is running ahead of schedule, you can put these extra things in, or if at the end of it, your client wants to renegotiate and say, yeah, we'll pay you some extra to do these things, you might include those as well, right? But that's basically the whole list of things your project might eventually encompass. Other things, what interfaces will be needed, right? So what other applications and systems you're going to connect with, and then thinking about who's going to use the app, right? What kind of technology they're going to use, what their default language is, what their level of experience is, which is all going to help you decide how the app will be created. For coding, right? Coding is writing the code to make the application work. Typically that's done in modules, right? So you build a bunch of modules that connect together. The idea with a module is simply that it's some kind of system that requires standard inputs and produces standard outputs. For example of modular code, Google search, right? You go to Google, there's a text box there, you type in some words, it generates a bunch of search results. So that search tool, that is a module, right? Google could potentially send those send that search query to any different system. So that's the nice thing about modularity. You can build your module to interface with different applications without redesigning the module itself. The other things, how the application is going to be set up in your system, right? So in terms of the presentation layer, the application logic layer, what data it's going to connect to on the database tier, and then so-called fourth tiers, application modules deployed as needed. We'll talk a bit about those at the end, but that's some system architecture stuff. We'll just have a few slides at the end of the lecture about that. Okay, testing. So in the testing stage, ideally testers confirm that essentially if you use the application correctly, it leads to a correct result. And if you attempt to use the application incorrectly, it does not produce any sort of result. Okay, so for example, if you have a point in your program where it expects a number, there shouldn't be some trick where if you enter in a very long number, the computer does unexpected things. Or if you enter in some non-numeric text like an exclamation point and a string of letters, it shouldn't cause the system to collapse. Okay, so valid commands are processed correctly. Invalid commands, they basically do not cause the system to collapse. Now, in reality, of course, testing tends to be extensive but not exhaustive. This is why, for example, you buy some computer game and you'll find that there are bugs in it. There are occasionally things that go wrong, right? In operating systems even, there are occasionally things that go wrong and they have to issue major patches for it. Most of the software that gets released these days is so big and complex that even the very smart humans involved in creating it and testing it can't cover everything. So they're just not going to catch everything. In particular, one of the things that happens, unexpected user actions or system interactions, they may often be overlooked. And other things that are just kind of impossible to test for example, like If a user is running a whole different set of applications on their machine, that may, for whatever reason, cause problems. For example, they may be using up too much memory, which may cause your application to not have enough, so it does things slow, and then portions of the system time out because they're waiting for actions to happen. Again, depending on the environment that you're using the application in, it may not exactly match the testing environment, and thus things can go wrong. But the idea is, at the end of the testing stage, you have an app that you feel is pretty solid. It's at least passed all the tests, so there shouldn't be any, major gaping flaws in it. But yeah, chances are there's still some bugs or vulnerabilities remaining, right? So it would not be true to say the expectation at the end of testing is that you've absolutely fixed everything and nothing can possibly go wrong. It's just good enough to be released for ordinary use. The release stage, of course, is where you release it. Where you say, okay, here's the application, try it out, use it, let us know how it is. So the implicit expectation is going to perform as expected, but in general, you don't get a lot of guarantees about that. They say, here's the product we're letting you use or we're selling you. We can't really swear that it's going to be perfect in all cases, okay? But what they can assure you is that it won't be used by the organization for malicious purposes, right? So for example, if you install Zoom on your machine, yeah, there's stuff could go wrong with that. But one of the things, basically the guarantee is that the good people who have produced Zoom, they're not going to use that to say steal passwords off of everything from your machine or steal your credit card numbers, that sort of stuff. Okay, now the 3 release stages are alpha, beta, and stable release. So alpha, as you might guess, happens first, and that means testing by the designers themselves, so internal to the project, okay? Beta is where it's released, so beta follows after alpha, and there's 2 flavors of beta testing. Closed is where the application is tested by a select invited group of users. So, you send out some email thing, we're looking for 100 people to test this, or maybe it's somewhere else in the business, right? You get a small set of potential users of the application. And then open beta is testing by the broader public. Basically, you post it up somewhere and say, here's our application, come use it. If things go wrong, let us know, that sort of thing. And then stable release. Stable release is where you say, we're past the testing stage, we're past the alpha stage, the beta stage. Now we think it's good enough for everyday use, and we're going to send it out there. And the stable part means they don't foresee making any major changes, right? With beta, there's the assumption that, yeah, it probably works well enough, but there's a good chance we might make some significant changes to how it's set up. But stable release is going to be, stable. And maintenance. Okay, so maintenance is what happens afterward. The product has been released, but you go back and retool it a little bit. So things like adding new features. If a lot of users are clamoring for certain features, yeah, you might put in some of that. Otherwise, improving performance, fixing observed problems, that sort of thing. So issuing patches for it. You also might develop, add some changes to go with new technology. For example, if there's a new version of HTML, which occasionally happens, right? So we had our last round, HTML5, released in 2014. There are periodically updates to scripting languages that might invalidate part of your application. So yeah, those things happen. If you want to keep using your application, you'll need to make updates there. Connection speeds, right? What's feasible at a high connection speed might not have been feasible earlier. So it could allow you to include some extra features and other hardware and software changes. Okay, now every time you do maintenance, that basically brings your project into a new design cycle. So it's sort of like a mini project all to itself. You plan through the things you're going to add, you have to code them in, you have to test that. Same kind of circle, right? And that might entail a new round of testing as well, some new beta testing. Okay, but that's the basic process, right? So zip back here. That's what we go through: planning, coding, testing, release, maintenance, and rinse and repeat as long as the application remains active. Okay. So this is a good time to take a pause. Let's do that. We're going to pause it. Okay. Any questions on any of that stuff? I hope it all makes sense. Oh, look, we have more people. Any stuff?
As for now, it's pretty straightforward.
Yeah, okay, well, good. Okay. All right, well, let's resume then. There we go. Okay. Sorry, I'm bouncing around a little bit here. Okay. So, technologies. What can we talk about? So this is the way that your applications are set up on the business side of things. So your standard two-tier technology, you don't see that much anymore. Okay? It was big through the 80s and the 90s. It started to get phased out, but we can still talk about that a little bit. So I'm gonna drop into Paint here for a moment, because everyone likes Paint. Okay. So here we are in Paint. So,
Excuse me, Professor. When you mean by phased out, you mean that it's no longer in use?
exactly. I mean, there's places where it is still in use, but it's not the standard way to do things anymore. Okay, so here's server, here's the client, ta-da. Okay, the idea with client server, couple things. Number one, all the necessary data and applications for a given client are kept and run on a particular server, right? On a particular machine. Right? Good. This is fine as long as it remains achievable, right? But you have some problems. I'm going to connect these. I don't know why I didn't connect them. Okay. So number one, so potential problems. What if you have a whole bunch of clients? Not like a few dozen or maybe even a few hundred, but imagine if you're like Facebook and you have a few billion. Okay, that becomes a big problem. I'm trying to get here so the glare on me isn't too much. For some reason, it really is. Okay. I don't know. You'll have to live with it, I guess. Okay. What if you have a whole bunch of clients, more than could possibly have their data managed by, or have their apps and data managed by one machine? On one machine. Right? So think of Facebook, for example. Facebook, for example, has literally exabytes of data, okay? 1 exabyte equals 1,000 petabytes equals 1,000,000 terabytes, okay? And a terabyte is about a typical hard drive these days. So literally 1,000,000 hard drives worth of stuff. That's not really feasible to keep all on one machine, okay? The other issue, even if you want to split up the data or split up the apps, but keep the data all up to date, it becomes a huge problem for that number of users, right? Basically, anytime someone changes something, that change has to be immediately echoed everywhere, right? To all replicas of the system, of the data. So these are the essential problems. Client server doesn't scale well. If you have too many applications to run on one machine, it's not going to be feasible. If you have so much data that you can't store it on one machine and you're going to have a bunch of different connections to other data storage devices, well, you still run into that same problem that if you have many users, they're all going to need to access that same data, And if you want to keep your data integrity, basically you want to make sure that your system is giving you the right answers. Every time one user on one machine makes a change, that change has to be recopied to all the others. So again, it's not really feasible for large scale systems. Where it could still be used, where it's still useful, okay, small, highly secure private systems, right? If it's something that doesn't have a lot of users, and if you want to, you know, if you're not connecting to the internet really, and you're not going to have to worry about these scale problems, it's easier to maintain security as well, right? You say, well, once you're in it, you're off the internet, but our team can still work. So something this, you know, think of again, some highly secure research facility, something like that, might potentially use client server systems, but they're pretty rare these days. Okay, other one, okay, so we'll go back, excuse me, I gotta switch my share here. Now we're gonna go back to our slides. Okay. We're gonna slideshow, ta-da. Okay, so that was our two-tier technology, our client server. And the basic way it works, right, there's a database machine there and the applications are running on the same machine. You send a query to the database returns the data, and the application processes it. Quite possibly the application is residing on the client machine, though not necessarily. Okay, but that's the overview of two-tier, and it's not really that important because there's a good chance you won't really see it. Three-tier though, or the so-called N-tier technology, that is one that's out there, although even that's been advanced upon a bit. So we'll talk about this one. So three-tier system has three kinds of tiers. So a tier just means a group of machines that are doing the same kind of task. So one is the presentation tier, right? So all of the different users of the system, they're all the presentation tier. So think of it in terms of, say, Facebook. You have your phone or your laptop, you're using Facebook on it, that's a presentation tier machine. The next tier is the server tier. So the server tier is where the applications actually run. So all of the applications that Facebook is running, whether it's for things like photo uploads or playing Candy Crush, whatever, those are all running on servers somewhere, okay? The last one is the database tier. So any data that's external to the application. For example, all the photos that you've uploaded to Facebook, Facebook has to store them somewhere. Well, they get stored in machines on the database tier. All right, so we'll draw a picture. And while I'm drawing the picture, we'll see While I'm drawing the picture, we'll talk a little bit about, I don't know what's, oh, there it is. Part of the problem with using Paint is that the screen share thing blocks up some of the essential tools, so I can't always see what I'm doing. Okay, so we'll start with this. Okay, so here I'm going to say DB for database. Here I'm going to say application, and here I'm going to say client. Now, one of the funny things about N-tier architecture is that you will always see different names for these depending on which vendor you're using. So for example, some might call the database tier the data tier, or the database tier, or even the storage tier. The application tier might get called the server tier, or the application server tier, or the application logic tier. And the client could, you know, be called the presentation tier, or the, you know, the client tier. So there's tends to be different names for them. It's a little strange, but like I said, you get the idea. This one, regardless of the name, data. This one, regardless of the name, is where the applications run. And this one is where the clients are. In that sense, it doesn't really matter what you call them. Okay, so the first issue with N-tier that it tries to solve, I'm going to say this. What if I have a bunch of clients? Okay, so I have a bunch of clients, lots and lots and lots of clients. And they're all connecting to this application, right? That's fine so far. Looks a lot like client-server architecture, right? Or at least it should. Okay, if it's all connected to one database in the back, that's fine. What happens when a user wants to switch to a new application? Well, chances are they're going to go to a new machine, right? That application is going to be running on a separate machine. So when this user, for example, say, oh, I'm not going to use that application anymore. Now I'm going to use this one. I go to a new application, right? I get connected to a new server. Likewise, I might still stay connected to the same database machine, or, right, I might get connected to a different one. So we're going to draw a little bit there. Okay, so these are the possibilities. N-tier makes it very easy for users to switch back and forth because it's built into the system. N-tier makes it easy to switch between applications and data sources. Okay, and sure, in a client-server system, right, in a two-tier system, you can switch to a new data source. It's a bit of a hassle. But here, what happens in this kind of structure, I'm going to draw a picture. So I'm going to draw this green box. This green box here, this is what the enterprise owns. For example, if you're talking about Facebook, Facebook has this structure. Once you're inside, right, you're connected to an application, you're already inside Facebook. They already have your access credentials. They believe you are who you say you are. So they're not super worried about switching you to a new application at that point. It's easy. Whereas with client server, since you're connecting to an entirely new machine in a new administrative structure, you know, usually they don't pass off those credentials. Usually they might say, well, you know, we have to go through some stuff to verify who you are because you're connecting through an entirely different machine. And the reason why, I'm going to get rid of this for a second. In practice, what actually happens, see, we can scrunch this. Let me show you. Everybody who connects joins through some interface. Okay, so I'm going to draw that here. They all go through some common interface. So when you go to facebook.com, they get your credentials, and then based on that, right, they're going to connect you to whatever application is appropriate. And so since they already have your information here at the interface, you know, they can very easily switch you to a new application. Likewise, any of these application servers can connect to any database in the back. And again, because that's all owned by the enterprise, there's not really much of a security thing. So there's sort of a hard outer shell here at the interface. But once you get inside it, you can do a lot more stuff more freely, right? The system is not going to be that worried about connecting you to a data source. So for example, in terms of Facebook, this gives you the possibility to easily and quickly access, say, your own photos that might be stored on one machine or somebody else's photos that might be stored on a different machine. Okay, with client server, that would be very difficult. It wouldn't really be built into the system. Every time you wanted to look at some data that was on a different machine, you'd have to disconnect from your current server, connect to the new one. They'd have to verify your credentials. It'd be a big hassle. Okay, so N-tier architecture lets this sort of thing happen easily. And the big players, right? The big guys like Facebook and Google have been doing this for a long, long time. Basically, it's what enabled their large scale in the first place. Okay, so their competitors were not always able to figure out these problems or devise effective solutions, but Facebook and Google did, and that was key to their success. Okay, but now N-tier architecture is pretty standard. In fact, anything you do in the cloud is probably going to be something like this, but we have a little bit more to add on. Okay, so I saw there was a question in chat earlier. We're going to pause it for a second. I'm going to address that. Let's see. Okay, so recording again. Okay, so here we'll walk through a little bit of the three-tier details. Okay, so the presentation tier, of course, is the client's computer. So that's the hardware. The software for web apps, it would be the browser, right? Because web apps run within a web browser. The client application, also anything that runs in the browser, you have to have that. So the way it works, receives input for the application tier, accepts output from the application tier, and any purely local actions, like when I grab that bird in Angry Birds and I put in the slingshot and pull it back, that's purely local. That's all handled on my machine. You wouldn't, the game would suck if for every little fractional pixel of a change I made, it had to send a call to the server, ask for some numbers, the server sent them back. It would be really slow and sludgy feeling, right? So certain things that you want to happen quickly, they're going to be handled on your local machine. Now, some of the trade-offs involved in application design. Number one, you want to minimize data flows to and from the application tier. So whenever possible, if something can be handled locally without too much trouble, you want to do that. Okay, and that's a big part of why we use client-side scripting like JavaScript, right? It allows these applications to do their thing locally without any involvement from the server side. The other thing, though, you also want to minimize the demands on the client's computer, right? Things like CPU cycles, hard drive space, battery life, that sort of thing. You don't want to put too much stress on the client because they're going to be unhappy with that. Number one, if the application is pretty intense, then it's going to make it difficult to do other things. Number two, if people repeatedly see that using some applications sucks their battery down fast, they might quit using that. Okay, I know Apple lately has had a bit of a problem with that, with the battery life issue. Yeah. Okay, so those are the trade-offs with the presentation tier. The application tier, the hardware is servers. Okay, so the software that's running there is the application logic. So whatever application you're running, like the thing that lets you upload photos to Facebook, that's what's going to run on those servers. And of course, you're going to need interfaces with other applications and tiers. For example, if you have this photo management application in Facebook, it has to interface with the data storage system so that when somebody uploads a photo, it can direct it to the proper database. Likewise, things like checking for prohibited content. There's probably an interface there and it's handled as a separate application. So once you upload something, that photo management application, kicks it off to that check off process. And then once that process returns, says, yeah, this picture's okay. Then Facebook says, okay, great. Now I'm going to do all my usual stuff with it. Okay, so any kind of software you have, yeah, you're going to have that interfaces with other applications and other tiers. So some of the trade-offs you typically see there at the application tier, providing whole applications versus modules. So we'll talk about that shortly. That's one of the descendants. So if you have a big application or application suite, do you provide the whole thing or do you only provide a small part of it that users need? Other things, more features, more problems, right? So this is where the complexity issue comes in. If you try to build an application that does more stuff, that's going to create some problems. So number one, development speed. The more things you want to include in your web app, the longer it's going to take. And, the more money it's going to cost and all that. It's also going to require more testing, right? So the more things you put in your application, the more complicated it gets. It's going to require more testing, and it's going to be increasingly likely that some of those vulnerabilities go through. So if you have a very complicated application, well, hopefully you're not handling any data that needs to be super, super secure on it, because there could be problems. And last, performance for typical and optimal users, right? So anytime you're developing an application, you're going to be putting in some features that a lot of people aren't going to use. For example, Excel, right? There's a whole lot of stuff in Excel that most ordinary users never use. For example, the ability to write macros, right? Little sort of mini applications within Excel. You can do it. UIC, we got a class, I believe, IDS through 331. You can learn how to write macros in there, but most users don't use them. So question is, how much effort do you put in designing a feature that's probably going to be used by a small subset of users? Well, that's one of the design decisions. And last, security versus ease of accessing data, right? So more security is a good thing, right? People like their data to be secure, but they don't like all the hoops you got to jump through to provide that security. For example, if you had an application that every time you logged into it, it had to send you code to multiple devices in different locations, right, to a particular laptop and your smartphone, and you had to respond within a minute, and you had to do a retina scan to prove that, you know, it was actually your eyeballs that was looking at the thing. Yeah, it would be pretty secure, but it would also be a big hassle, and people wouldn't like it. In extreme cases, you might even require that sort of check every time you went to a different page in a website, or every time you requested a particular batch of data. Again, it would be very secure, but it would be a big headache. So these are the design trade-offs, right? Again, so something like Facebook, they say, well, what's the most damage somebody can do? I guess you could delete a few pictures, that would suck, but that's a, you know, or you could send a nasty, I don't know, you could send a dick pic to somebody's grandma or something like that. That'd be pretty awful. That's about it though, right? So Facebook, you're not looking at serious damage. So their security, yeah, they try to provide security, but they definitely favor ease of accessing data. On the other hand, some of these banking applications, right, they're talking about real money. And they know that, you know, the criminal activity that it attracts isn't just a nuisance, it's actually, you know, potentially very, very serious. So if somebody could hack their wire transfer system, the banks could be out many millions very quickly. So they definitely want to lean toward the side of more security. And since it's a fairly small set of users that are even accessing these services, they're okay with that, right? So for example, if you want to do a wire transfer to somebody, in many cases, you can't do it instantly. You have to schedule it, say, sometime the next day, so that the actual account owner, if there's something fishy about it, can look and say, hey, I didn't order that wire transfer, and the bank will have time to stop it. Okay. Database tier. So in the database tier, you get server clusters, basically groups of servers, load balancers that distribute the new connections over that set of servers, so it doesn't get super busy on any particular one. And you might also have some what are called in-memory options. So you might have very popular data stored in RAM where it's easy to get to. So the link I have here is from Oracle's ×10 system, which is basically a big bank of RAM for very popular requests that is periodically updated to permanent storage. Any changes that happen in that RAM, they will eventually be updated to hard disks somewhere so that it stays permanent. Anyway, but that's part of how, you know, they manage the scale issue, is that what you tend to see is certain bits of data are very popular. For example, if there's a new hit song and there's something about it on Facebook, Facebook expects, yeah, there's going to be a lot of people looking at this. Or if it's the day after the Super Bowl and everybody's looking at the Super Bowl commercials, again, those are the sort of things that might get stored in RAM so they can be more quickly delivered to a large set of users. Okay, so there are a lot of different software providers there. Oracle is the big one for relational databases, but again, many, many others. And another issue is what kind of database you're going to have. Are you going to have a relational database where it's very structured, and in your database tables, every record has the same set of fields? You can fairly efficiently look up data. On the other hand, a NoSQL system is going to cut some corners on there. So it may be more efficient in terms of storage, but perhaps not in terms of retrieval, or perhaps that you have to keep your data fairly simple in order for it to be equivalent in terms of retrieval. Where it might be useful, a simple one is talking about pictures. So in a relational database, since every record is going to have the same structure, this becomes a bit of a problem for images, because some images are large, some images are small. Your database is going to have to allow a size in each record for the largest possible image, and the rest of that is just going to be wasted space. NoSQL systems, on the other hand, they can just pack in the images one after another, and they keep a list of here's where each thing starts and stops. Okay, so it's not so much of a headache, but the difference is relational database, if you want to put in a whole lot of extra kinds of data, it can manage that better. A NoSQL database, not so much. Yeah, that's the trade-off. So it's basically flexibility versus, I want to say efficiency, but efficiency doesn't quite capture it. I would say the ability to execute complex queries quickly. For example, suppose in NoSQL, Well, in a relational database, for example, you know what fields every table has. Okay, you know that, for example, if it's a customer table, if you have defined the fields last name, first name, phone number, address, zip code, you know all of those data fields are going to be there for every record in the table. So it's easy to do a cross-check with another table, and you can ask questions like, give me a list of all the customers who have bought a motorcycle if they reside in the zip code 60614, right? And you can get some data about that. For a NoSQL system, though, the tables don't have that tightly controlled of a structure. So you don't know if every record has that field. You don't know where that field would be located in that record if it does have it. So the scan through process is going to take a lot longer. All right. Anyway, in general, so that's an example of the trade-offs that are involved. So different database structures can allow for greater speed or greater volume or be cheaper or more secure or more reliable. There's a lot of design trade-offs built into that. If you take some advanced database class, you might get into some of those things. But last I checked, IDS 410, our database course, doesn't really do those. Those are more of a master's level course thing anyway. Okay. But if you're interested, I have a link here. It's a few years old to a Salesforce article about how they handle their tremendous size. And you can find similar articles about Facebook or Google or any of the other big operations. Okay, so pros and cons of the 3 tiers. So one of the pros of the N-tier system, the 3-tier system, is that it's modular. That means changes within a tier tend not to affect others. So give an example, if Facebook wants to change its photo checking system, right? When you upload something, they look to see if it's prohibited. If they make changes to that, that change happens only in that module. It doesn't affect any of the rest. So the whole rest of the system operates as it always did. So that's nice. That kind of modularity makes it easier to implement those changes. One of the changes with client server, though, since everything resides on the same machine, if you take a change to one part of the system, you're automatically reducing the resources available to other aspects, right? So other applications, other data storage, whatever, that can potentially create problems. Another thing, better security. So since in the N-tier system, users only have indirect access to the data, right? They have to go through the application tier to get to stuff. In client server, there's a security concern that users have direct access to data. They're in the machine, essentially, and if they somehow manage to look at data they shouldn't be, well, hey, they're right there. On the other hand, in N-tier architecture, when you make a request to a database, it has to go through the application. So you actually have to create some kind of query that's correctly formatted, but somehow slips through the net and gets you to look at stuff you shouldn't be able to, which is a lot less likely. Because of this modularity, development and maintenance are simpler. Again, any changes you make to the system aren't really going to, any changes you make to one module aren't going to affect the whole rest of the system. Okay, and scalability. You can provide scalability in different aspects internally. For example, if you find that you have a lot of clients and you need more servers to run applications on, boom, you can add in more application servers and not have to add in more database more database machines. Likewise, if you find out that people are uploading, you know, an exabyte of, or a petabyte anyway, of photo data every day, guess what? You don't need to add on a whole bunch of application server machines. You just add on more data storage devices. In client server, right, an ordinary client server, if the data exploded like that, you'd have to buy many more new machines and they'd all have to run all the applications. So you'd need more capacity that way. Okay, so basically, the nice things about N-tier architecture, it's more modular, so it's easier to make changes, whether it's in terms of changes in how it operates or actual changes to the components themselves, and it's more scalable. It works better as it gets bigger because of that sort of flexible connection. The cons, compared to 2-tier, well, number one, it's obviously more complex to design. So there's that hurdle to jump over. I mean, if it had been easy, then all of the companies like Google and Facebook would have done it, but they didn't. And last, potentially slower response time. So because you're going through different layers, right, you're going through a server tier to reach the database, it's not going to be as fast as if you just go straight to the database itself. So for some kind of specialized systems where speed is very, very important and you can ensure that, you know, only very trusted users will be accessing the system, then yeah, client server might work better. Okay, moving on. Last thing, right, module delivery. So this is something that's come out in the last few years, maybe been big in the last 5 years or so. Instead of deploying entire applications, you can deploy a small application module with basically the minimal operating system required to actually run it. Those are called containers. So if you've heard of Docker or Kubernetes that do these kind of containers, yeah, that's their thing. Okay, so we'll talk. The first model is the virtual machine. So the idea with a virtual machine, it's essentially a copy of an entire computer. Now it's virtual, so those copied components might exist on different machines, right? So for example, the application might run on a server, but the data storage might be on another machine. So it's virtual. All the pieces are there, but they're not necessarily there in one particular machine. The thing about a virtual machine, it has a complete operating system, which means just like the operating system on your laptop, it can support a large range of applications, right? So if you have Windows or Mac OS, whatever, you can run a whole bunch of different applications on that. The downside, compared to a container, takes longer to deploy, and you tend to have fairly low utilization, right? Even though you have the capability of doing a lot of things with it, at any given point, you're probably only doing a tiny, tiny fraction of those possibilities. So the next logical step is the container. The container has a very minimal operating system, just exactly what you need to run the particular application, right? So suppose you want to run Microsoft Excel. Well, in a virtual machine, you would have the complete Windows operating system, which would let you run Excel. That'd be great, right? In a container, you just take those few specific parts of the operating system that are required only for Excel, and you deploy them along with the copy of Excel. So the nice thing about it, compared to a virtual machine, it's very quick to deploy. Some of the simpler ones might even only take a few milliseconds, and you get very high utilization. So this operating system, right, requires a lot of space on a server to run. So if you can cut a lot of corners off of that, then you can have effectively a lot more things going on your server without massively increasing the amount of RAM you have. The downside of containers, though, anytime you switch applications, that's going to require a new deployment, right? So you have to get the new part of the operating system that you require for that. So the question is, which is more appropriate? Well, if you have a virtual machine, that's good if you're switching back and forth between a lot of fairly complex applications, and building containers for them would take a little while. Containers make sense if you're flipping back and forth between simple applications, or if you're really only deciding to use one application over the course of the day, then it's just there and waiting for you, and you don't need that whole operating system. Okay, so containers, if the applications are simple, switching is not a big deal. But if the applications are complex, then yeah, switching is a hassle. It's going to take a while to deploy a container. You're probably better off with a virtual machine. Okay, that's it. We're going to stop that lecture. We're going to stop the recording.